The first stages of the death of a star are the same, whether you're talking about a high mass star or a low mass star. So we'll talk about those two types of stars at the same time here. Now, a star is alive when it's burning hydrogen in its core. That's what it means to be on the main sequence. Once that hydrogen in the core runs out, the star goes from you think of it as a living star to a dying star. Its days are numbered at that point in terms of whether or not fusion will keep going. As a reminder, when we talked about the formation of stars and properties of stars, one of the determining factor in the luminosity of a star and its temperature when it's on the main sequence is the mass of the star. And that mass continues to play an important role as the star leaves the main sequence. So what do I mean by low mass and high mass? Low mass stars are stars that are 2 times the mass of the Sun or less. High mass stars are stars that are 8 times the mass of the Sun or bigger. And that does leave a pretty big intermediate range there, stars between 2 times the mass of the Sun and 8 times the mass of the Sun. What happens with those depends on the details of that individual star, what its precise composition is, and that sort of thing. Now at the end of the main sequence, if you look at just the core of a star, and so this picture in the lower right here, that's not the entire star, you're just looking at the core. That core is maybe 1% the size of the entire star, maybe up to 10% depending on whether you're talking about a low mass star or a high mass star. But eventually the hydrogen runs out in the core of the star. You end up with pure helium because hydrogen is fusing into helium while it's on the main sequence. You have a shell of hydrogen that's around that helium that is hot, but it's not hot enough to fuse at this stage when the star is just at the end of the main sequence. Now, when hydrogen fusion stops in the core, the important thing that changes inside the star is that you no longer have a sort of a thermostat to regulate the temperature of the core. When fusion is ongoing, then if for some reason the core was to contract a little bit and heat up, that increase in temperature would cause an increase in the fusion rate, which would generate a bigger pressure, which would push back out until the core was back to its normal size. When the hydrogen's all gone and there's no helium happening in the core, if the core for some reason starts to shrink, it's going to continue to shrink. And in the case of a star leaving the main sequence, when that fusion stops, suddenly gravity's winning out over pressure. So gravity pulls inward, the core heats up. It's not hot enough for fusion to happen in the core, turning helium into something heavier, because that requires an extremely high temperature, 100 million degrees or higher. Now, it does get hot enough in that thin layer of material outside the core, this layer of hydrogen that's just outside that helium core, that gets heated up enough that fusion starts in that shell. That makes the core even hotter, and as a result, during this phase, the inside of the star is heating up quite a bit. Now, the effect of that is because you have a much higher temperature in the core, you're releasing much more energy from the core, and that energy's got to get out of the star. That means that the luminosity of the star is going to go up quite a bit. That energy, that heat coming out from the center of the star, pushes the outer layers of the star out. So as you heat the interior, just like any gas, the outer layers of the star expand. Radius goes up by something like a factor of 100. Now, the surface area of the star grows by a factor of 100 squared, which is 10,000. That's a lot more than the temperature, a lot more than the luminosity goes up by. The only way that can be the case is if the temperature of the star goes down. And so you have two things going on. The star is getting cooler, but it's getting much larger, and the star is becoming a red giant. Here's a cartoon showing the Sun as a main sequence star in the upper left there as a small dot. And next to that, the Sun is a red giant. It will be 100 times larger as a red giant than it is now. Now, when I say 100 times larger, I don't mean 100 times more massive. It's exactly the same mass, or virtually the same mass as it is now. It's just puffed up to be much larger. Now, in a star cluster, you can see this sort of behavior happening. The time it takes for the Sun to go from being a main sequence star to a red giant is huge. It's 10 billion years from the time that. Let me back off that. So when the Sun arrives on the main sequence, when it leaves the main sequence, is 10 million years. The for the time it takes for the sun to go from being on the main sequence to being as big as it's going to be as a red giant is several million years. So there's no way we can watch an individual star do that. But if we take a picture of a bunch of stars, then we'll catch some of them in the act of going from main sequence to red giant, and we'll see pictures of that a little bit later on. Now, eventually, if the core of the star gets hot enough to a temperature above 100 million degrees Kelvin, then helium fusion starts to occur. And there's a diagram there showing what happens in helium fusion. The details really are not that important. The main thing to realize is that each one of these helium fusion reactions that happens releases much less energy than a hydrogen fusion reaction. So that fuel that lasted a star like our sun 10 million years, or sorry, 10 billion years when it was on the main sequence burning hydrogen, well, when it's burning the helium into carbon or into oxygen, that fuel is going to last much less time, maybe 10 million years or 100 million years. Now, it's at this point, once the helium fusion starts in the core, that you start to see a difference between low mass stars and high mass stars.